Next speaker is, as you can see, improvements to the Geoid model by Dr. Gerry of National Geodetic Survey.
All right. Oh, thanks, Roy, for that fabulous introduction. All day I've heard how Jerry's going to talk about this, Jerry's going to do that, and no doubt has raised your anticipation level to the breaking point. Meanwhile, my anxiety level is going up tremendously because every time I hear my name, I snap out of my doze and I say, what? Okay, so if I don't talk about what you're expecting, please let me know. This talk will also prove that just because I'm Dan Rollman's supervisor, and he really did all this work and put it together, doesn't mean I know anything about what he's doing. So I apologize in advance for any missteps I make. And no doubt Dan is sitting somewhere sweating bullets right now that I'm going to screw this up. I've kept Dan's outline because it's a classic example of how the priesthood of sacred knowledge tries to preserve its sacred knowledge and not let you know what's going on. I thought this is great. None of these acronyms probably mean a great deal to you or to anyone else, but really what we're looking at, we're going to follow the steps by which the gravimetric geoid is computed, and then I'm going to talk about how we get the hybrid geoid out of that, and then some things that are coming up later on, and the geoid is in there as well. So you could stare at this all day long. You still won't know what it is. I'm sorry, what? Really? I hear myself just fine. Is that a little better? Is that a little better? All right. Well, I hear amplified sound. In fact, I thought I was talking too loud. But if you can't hear me at all, raise your hand. Okay. All right. Well, anyway, that's the first step, our outline. We're going to talk about how the gravimetric geoid is computed. And as the name implies, the gravimetric geoid is computed from knowledge of gravity. As you may know, well, you may not know, that there is a process by which we do this. It involves integrating all the gravity around you. And to do that, you think, well, what gravity is most important? Well, obviously it's the gravity in your immediate vicinity. And I don't need to know what the gravity is on the other side of the world. Well, that's not correct, because whereas it's further away, there's a lot more of it. So you need to know the gravity everywhere. And what's important to do this is, or what we have, the resource we have are these global gravity models that come from spacecraft. There's been a series of them. The most recent, I think, is the GRACE satellite, from which the global gravity model that I'm going to show was used to compute. And so locally, we're going to use all these gravity points that have been collected, but we're going to model the globe from these global models. And you'll see why they're important. The other aspect, the other thing that we're going to use are these elevation-dependent models. And there's been a number of also space flights where the local terrain has been computed. And this is also important for correcting our surface gravity data as well. The hybrid geoid, as you'll see later, I'm going to show a beautiful diagram that explains this, starts from the gravimetric geoid. And we need to have benchmarks, ideally, that would be well distributed, and you'll see how how well that works, and so on from that. Anyway, these are the differences in the global gravity models from the satellite data. You can see the first one up there. Well, EGM-06 is the most recent one that's computed. And we're comparing that to EGM-96, one of the earlier ones, and you can see the differences involved. In particular, there's this sinusoidal variation that goes across CONUS over here, which we sort of knew about before. The point I think we want to make is not just the importance of these global gravity models, but the fact that they change with time. Doesn't mean that they're actually time dependent or that we're recording any time dependence, just that our ability to record these accurately is constantly improving. The other concept you need to get across here is the wavelength of these models. Because they're at higher altitudes, several hundred kilometers, on the surface of the Earth, they have what we call a wavelength of several hundred kilometers. They don't see fine detail, which makes them useless for your work, but still renders them very useful for the sort of global integrations that we need to do to compute the gravimetric geoid. So we would expect that future space flights are going to give us new global geoid, global gravity models. The difference is with the current one, e.g. M06, will probably be smaller than what you see here. That would be progress. We have about 2 million individual gravity points in our database from which the gravimetric geoid is computed. These are the local points that I was mentioning earlier. They're used in conjunction with the global models that you just saw. They're thrown into the equivalent of Stokes integral, if you remember your physical geodesy book, if you ever took it. Anyway, that's how that's where these things go. And as you'll see, we're trying to show the density here. The density is not too bad over most of CONUS. We incorporate some data in Canada as well, and you'll see the shipboard data, of which we have a lot of data along the coasts. But that's deceptive because it doesn't really go everywhere we want it to go. It doesn't come right up to the coast. And later on, I'm going to talk about some of the systematic problems that occur in these data sets. But that's the data that's used for the computation of the gravimetric geoid. Before you use any data, you need to ask yourself, gee, is my data any good? How do I know if I have any outliers and this sort of thing? Well, all these gravity points are differenced from the predictions of the satellite-based global gravity. And generally, they agree pretty well. The surface gravity that was measured lies within a band of acceptability from what the satellites would predict. However, where we see outliers, they do get thrown out. Lots of data gets thrown out. Now, for Geoid 09, which is coming up in our discussion, a huge number of points were thrown out, particularly in the Rockies over here, because we did not include the terrain modeling. There's obviously, because of the altitudes, there's a huge amount of variation in the surface gravity. Not applying the crane correction made them appear anomalous with respect to the satellite gravity, and they were tossed out. We do now have the terrain models, and Dan has the time to apply those terrain corrections, so we expect that data will be included in the next gravimetric geoid that's coming up either the end of this year or early next year. But anyway, this is how the gravity data gets filtered. In addition to filtering the data point by point, the individual gravity surveys, a survey obviously was taken within a more or less contemporaneous amount of time by a certain number of individuals and instruments and constitute a coherent survey. We look at the surveys as well and see where they may be biased with respect to the satellite data. Where the surveys covered a large enough physical area, they can be corrected by the satellite data. So the whole survey is biased up or down to bring it into alignment with what we think it should be with respect to the global gravity model. So they're recoverable, but where the surface gravity surveys are too small in extent, in other words, the wavelength of the global gravity model is much bigger than the survey, they cannot be brought into alignment. This particular problem is what GravD is going to fix. We're going to have all this aeronautical survey data, which is going to be as certain virtues which are wonderful, and primarily they're going to be used to bring the surface gravity surveys into alignment so that we will be able to compute a much more accurate gravimetric geoid. The result is, as you see here, and we may have seen this before, this is the gravimetric geoid 09. It looks pretty, but it doesn't mean anything to you. You just see a lot of contours and circles up there. Check my notes here, make sure I don't leave out anything Dan wanted me to say. The differences are probably more significant, and I think we showed this before, the gravimetric geoid 09 with respect to 03. And again, the amount of point data that was thrown out in 09 is shown here in the Rockies. This was erroneously, or probably should not have been included in 03, but it was anyway. We thought we knew better, and we're going to throw it out over here. The altimeter, the satellite altimeter people made some corrections to their data, their results as well, which is what shows up over here. Anyway, those are some of the differences. We expect those to continue as other models get computed. All right, in summary, I want to point out that the gravimetric geoid is a geocentric phenomenon. NAD83 and NAVD88 is not. They are off. They are not geocentric models. One of the transitions we're making in 2022 that you heard about is to go geocentric. It's obviously a lot more convenient since most of the way we compute positions now is satellite-based, and satellites know where the geocenter is, even if we don't. It's just a much more convenient way to do things. So we want to make that transition ultimately. But keep in mind that if you ever were to go to the gravimetric geoids, they are centered in ITRF. And you typically have a 1 meter height difference between heights in ITRF and NAVD88 heights. So don't screw that up. Use the geoid numbers, not the geoid 09 numbers, not the gravimetric geoid values that you see here. All right. All right, I think Dave showed something like this. Now I'm going to give you my version of what what's going on in this plot. We have now arrived at the point where we have a perfectly reasonable gravimetric geoid. One of the virtues of this geoid is that, gravimetric geoid. Think of it as an equation. Anywhere on the surface of the Earth, I can know my position using GPS. That means anywhere I can plug in the latitude, longitude, and I can get the geoid, or I know where I am on this geoid. I can get the distance down to that geoid because I have the ellipsoid height from GPS anywhere, and I know the geoid, gravimetric geoid height with respect to the ellipsoid. So I know those anywhere I want. Well, that's wonderful. But you guys don't live on this gravimetric geoid. You live on this NAVD88 surface. The problem is that NAVD88 is only defined where you have these discrete benchmarks. All right, that's okay. That's just the way NAVD88 was defined. That's not such a problem. But what happens if you're in between? And this is really the question we've been asking, is how do we compute our equivalent orthometric height, get down to the NAVD88 surface from somewhere on the surface of the Earth when we're not on a benchmark? All right, if everything was working perfect, this surface would have been right on top of that surface. They would have been coincident, but they're obviously not. If things are working pretty good, then the shape of this surface should be pretty close to the shape of that surface. So what we do, and what Dave was explaining, is that wherever we have benchmarks with good ellipsoid heights, we can say, we know the difference in height between this surface and this surface by virtue of this formula right here, is that these heights, these three heights, when combined with the appropriate algebraic signs, ideally would be zero, but in fact they yield some finite difference. And it's a least squares fit to the surface of this difference. Okay, that's called the conversion surface, and that's what's included in Geoid 09. That conversion surface is what you need to get from this gravimetric geoid surface over to NAVD88, using the assumption that the the shapes of these two are pretty close together. So how does that work? What do we need to do that? Well, you need well-distributed benchmarks. You would like to have them as frequent as possible, and obviously there's going to be places in the U.S. where the benchmarks are sort of sparse, and it's not going to work real great. The other thing we need are ellipsoid heights, obviously, so we need ellipsoid heights on the benchmarks. All right. Here's the distribution of the benchmarks that we used in, what am I looking at here? This is one of the earlier computations of the geoid, and I think the next one shows, okay, these are the ones that were used in 03, and now in 09, we're up to 18,000 benchmarks were included, including some in Canada. Anyway, you can see that the distribution, there's some states are very dedicated to getting their benchmarks surveyed, but obviously in the mountainous areas, it's pretty sparse. Parts of Texas is pretty sparse. So we don't have good coverage, so that the determination of that conversion surface that I just described is going to be much better in some places than in other places. In addition to that, we also depend on knowledge of the ellipsoid heights. Well, the ellipsoid heights are changing as well. Not necessarily changing with time, but they change with the national adjustments that we wind up doing. And what we're showing here is that the shift due to the 07 adjustment with respect to the previous adjustment. And you can see that there's areas of the country where the changes are pretty significant. And I wonder if this is, yeah, you can see it here, particularly in California, Minnesota, and Nebraska. And down in the south, we had some significant changes in ellipsoid heights. And again, it has more to do with the way the adjustments, what was constrained in the adjustments, than anything else. For example, the initial adjustment held the horns fixed. We didn't attempt to smooth out the boundaries between the individual states, but the next adjustment, 07, was a true national adjustment, and those things were smoothed out, so things were a lot better there. The next adjustment will use the coarse coordinates, and so we expect that to be even better than this. In any event, you saw this before. The conversion surface basically reflects the tilt that Dave was talking about from the southeast to the northwest. Again, I cannot offer any explanation what causes that either. It's just that we're living with it right now. And a big picture of Geoid 09, and you see some of the numbers there. Again, it's the difference, if we showed Geoid 03 right next to this, they would look pretty much the same. The changes are fairly subtle as you go across. And here are those changes between 09 and 03. And you see some significant changes in California. And again, this is where we had those circles drawn before. Big changes in ellipsoid height that were illustrated earlier. They also consequently yield big changes in the geoid. However, you'll see down here that there's big changes between the two geoids that are not related to big changes in ellipsoid height. And that's the reason why I think we've been talking about that all day. It's obviously due to the subsidence. A couple of height mod surveys have been done during the past decade. You see them illustrated here. And this is the information that went into the computation of Geoid 09, and you see the numbers here. And I think that's been discussed earlier as well, so I'm not going to elaborate on that. But if you have any questions about this later, certainly between myself, Renee, Dave, we can talk about any of that. There'll be some more satellite computations of the global gravity model coming up, and that's the next Future Satellite Goach here. We continue cleaning up the surface gravity data and applying the terrain corrections that I spoke about. And we have plans, obviously, with GravD. I'm going to say a little bit more about that, what Dave talked about. The next adjustment, I already mentioned that, and Opus database. GravD, I have to digress here. I showed earlier all those gravity points, 2 million points, and I showed the individual gravity surveys that seemed out of whack with the global model. You have to realize, and I certainly realize this, that you have millions of gravity points collected by hundreds of instruments, hundreds of different people over about the last 100 years. There is no way you could convince anybody that that's a coherent, consistent data set. It's just not possible. We've probably squeezed as much out of that data as we're ever likely to squeeze out of it. So there's no room for improvement with the current data set. I say that somewhat cautiously, but I think you get my point, is that it's just not going to work, all those different gravity surveys. There's got to be systematic biases between them, and there are, and there's tilts, and when you combine with that the shipboard data, which is on a completely different platform in a different environment, there's no way that that data could be coherent, consistent with the terrestrial gravity data. So it's just not going to work. There's only so far you can go, and if we ever want to get to a 1 centimeter geoid, it's not going to be with the gravity data the way it currently is. So what can we do? Since the 1980s, late 80s, we have more on and off been partners with the Naval Research Laboratory. John Brezina is a fellow there who was doing airborne gravity surveys for the purpose of computing geoids on the ground. He was, Naval Research Lab was doing this for a Defense Mapping Agency, what was then the DMA. And I think the first survey they did that I had anything to do with was in Greenland, and I was amazed that you could do serious work, gravity work from an airplane, using GPS to remove the accelerations of the aircraft and infer that down to gravity on the ground and compute a geoid. Anyway, so airborne gravity is not a new activity. It's been going on for a while, but it was new for NGS to think about this, and at least from my point of view, was to replace all these gravity points with the airborne gravity. Why? The gravity data would all be consistent. It comes from the same instrument, the same platform, and it would be more or less contemporaneous. It would be taken within a snapshot of a few years. That was the original plan. And those virtues are significant, and that is what would enhance the gravity. And that's almost the point we're at. But Dan convinced me that, well, what we really want to do is do that, but also do not throw away the surface gravity, because we need that to interpolate along the airborne tracks that we're going to use. So the direction to Dan was to say, okay, we want to get to a 1 centimeter geoid, work backwards to what do we have to do what do we have to have on a plane, how do we have to fly the plane, all the parameters of the flight to get to a 1 centimeter geoid. And that's what defined the operating parameters for GravD. It went forward from there. It's now a funded program. The planes are flying and data is being taken, and we hope that soon we'll have some data released to the public, and along with some of the initial results. Anyway, you've probably been reading all that while I've been talking, so I'm not going to read it back to you. But I think the plans are further summarized here, and you'll see, well, probably the visual is a little bit easier to see. It's color-coded by what we've done and what we've got coming up. But we've been doing a lot of work in Alaska initially, because Alaska had nothing. And we thought we would start there first and get that out of the way. Anyway, the plan is to do the entire country with GravD, and hopefully get to our goal of a 1 centimeter geoid, and we'll see. As I mentioned, we have a new adjustment coming up, which is going to be tied to the core's coordinates, basically the same vectors that were used in the previous adjustment, but now we're going to constrain the cores. And this will make the resultant ellipsoid heights and the positions more consistent with the way Opus is doing business right now. So, internally we have a little bit of an inconsistency, and presumably we're going to remove that. If things go according to plan, that'll be done by the end of this calendar year, and shortly after that, there'll be a new geoid based on those new ellipsoid coordinates. The application of the terrain corrections to the gravity data where necessary will also allow us to include more points in the gravimetric geoid. Say a few words about Opus database. One of the motivations for getting data that was submitted to Opus into a database was the fact that blue booking seemed to be such a labor-intensive activity. And in fact, the difficulty or the amount of work involved in blue booking and submitting to the IDB was probably the biggest hurdle for us to get data from guys in the field and get the data in. So we wanted to streamline that process. And that was the point of Opus database. As you see over here, we did not want to give up any information. We wanted to include everything that was important, but to make it possible to publish results within a day. From the time you submit the data, submit the metadata that we require, we can produce a data sheet very, very quickly. And that's the fact. I think we have over 3,000 points in Opus database now in about the last year and a half, 2 years. And it's our curve, our rate of submission is ascending. So I think that will fulfill its promise of being a very successful way to get data in. A lot of benchmarks that have been leveled have been included in Opus database. We've got, I forget the number, but there's about quite a few are shown here. And you see that well, it's hard to tell from just this plot, but we're filling in a lot of areas that were sparse originally, or we're getting some points in there. Dan has done a comparison of the points that are in Opus database with the points that were determined in the IDB. And, well, neglecting some outliers, really, what we're looking at here is a standard deviation of the conversion surface to the conversion surface for points in the IDB and points that were in Opus. And you think, oh, this looks bad for Opus. It's got twice the standard deviation that the IDB had. But you have to remember that what we're doing here is using the ellipsoid heights from Opus and the conversion surface that was determined from the IDB. Okay, so naturally the IDB is going to be more consistent. Even if these ellipsoid heights in here are seriously in error, the conversion surface will have to fit them. We just can't get around that. So this is an interesting number, but it's not a fatal number. On the other hand, if we look at points that are common to the IDB and are in the Opus database, but were not used in Geoid 09. And in this case, what we're doing is, okay, we take the ellipsoid height, the conversion surface, and we go to compute the orthometric height, and we compare to the orthometric height that's in the database. We find that Opus DB had a slightly better standard deviation than the ellipsoid heights in the IDB. I don't know why Dan has included this other one, since these were not previously observed and not included in the conversion surface, so I'm not going to worry about these too much. I think this is the most relevant comparison right here. In any event, we expect that the Opus DB points will be contributing to future geoids. Will they contribute to the next geoid that Dan computes? He's a little ambiguous about that. He's a very cautious fellow. I think he will wind up including them, but at the moment he's not committing himself to using this. However, for the geoid after GG12, I guess GG15, we certainly will be including the benchmarks in the from the Opus database. Anyway, this is the means by which we can densify our benchmark network easily and get you to give us that information and get it into the database for computation of the geoid. However, we have to keep in mind that even Opus database and good ellipsoid heights are not going to make up for subsidence and absence or the changing of orthometric heights. There's nothing we can do about that. That you just would need more leveling or to fix that problem. Anyway, some of the things we're looking forward to in the future are new reference gravity fields, the application of what we're talking about here is terrain models to correct the surface gravity data. We have some new high-resolution regional terrain models coming online that we expect to use. And of course, we're going to see more changes, just as we saw from 03 to 09. The next Geoid 12 will have additional changes, mostly going to come from the ellipsoid heights that are going to be computed in the next adjustment that we're doing with respect to the cores network. Lastly, another commercial for Opus DB. Anybody here has submitted anything to Opus database, been published in the Opus database? Yay, we got it. One or two hands. Okay, good. Anyway, everybody take a look at it and see. It's really simple to use, a quick, easy way to get your data, get your results published. But as I said, okay, this is great. But it's not going to help if we don't have the leveling. So we need better VTDP models to use with the gravimetric geoid. All right, that completes Dan's talk. Thank you. Oh, good. There's no questions. Okay.